So in today's video, we're going to briefly cover the notion of rewriting before integrating. And this is actually a very crucial notion that's going to extend to pretty much all of your integral calculus experience, because the first thing that you should do whenever you're integrating, whether it be a definite integral or an indefinite integral, is to look at how you can actually simplify the integral, how you can kind of re-express it or algebraically manipulate it in a way that will actually make the integration process much easier. And so as a quick review, for the reverse power rule of integration, if we're integrating x to the n dx, right? So just any polynomial function or any function raised to a certain power n, then the integral is going to be equal to x to the n plus 1 over n plus 1 plus c, right? And n, of course, as we previously mentioned, is just a real number, except n can't be equal to -1. That's just what this notation over here means, if that is a little bit confusing. And so let's go ahead and actually look at a couple of examples how we can rewrite before integrating, and then we'll actually go ahead and evaluate the integrals themselves. And so here we have, this is actually a question taken from an IB paper 1 exam, an HL Math paper 1 exam. So it's very crucial to get familiar with this type of concept for your IB and AP calculus exams. So we have the definite integral from 1 to 4 of 5 plus the square root of x over the square root of x dx. And so at first this may look a little bit kind of odd, and you may need to think about how to integrate a rational function, but really all you have to do is just simplify this. So we can rewrite this as the integral from 1 to 4 of 5 over the square root of x plus the square root of x over the square root of x. Right here we're just simplifying, we're just separating the term in the numerator. And then we can notice a couple of things. First of all, the term in the denominator, the 5 over the, so this first term over here, the 5 over square root of x, we can take that square root of x out of the denominator and bring it up, and then it will become 5 times x to the -1/2, right? We kind of re-expressed it as x to the 1/2. We re-expressed the square root as x to the 1/2, and then we brought it out of the denominator, and hence we have to switch the signs. And then over here, the square root of x over the square root of x. We're assuming, of course, that x is not equal to 0 because it's in the denominator. We can kind of just cancel this out, and we'll end up with 1, right? The square root of x over the square root of x is just 1, and then dx. And so here we have now a much simpler expression that's, we can just use our basic knowledge of the reverse power rule in order to integrate this. So this is just going to be equal to, we integrate the first term, that's going to be 5x to the -1/2 plus 1 over -1/2 plus 1. And then this plus 1 over here, it's just going to become x, right? Because we know that this is a 1x to the 0, right? 1x to the 0th power. We increment the exponent, and then we divide by that new incremented exponent, and we just end up with x. And here we're going to evaluate this entire expression from x equals 4 to x equals 1. This is going to be equal to 5x to the 1/2 over, this is going to be 1/2, right? So let's go ahead and just simplify this expression. We have the 1/2 in the denominator. When we bring it up, it multiplies with that 5, so we end up with 2. And then x to the 1/2 we know is just the square root of x. So, or not 2 rather, this is a 10, because it's a 5 times 2. So 10 square root of x. And then this plus x we just keep the same. And we're going to evaluate that from 4 to 1. When we evaluate it at 4, we get 10 square root of 4 plus 4, which is just going to be, what is that? That's going to be 20 plus 4, so that's 24. And we're going to subtract it from 10 square root of 1 plus 1, which is just 10 plus 1, which is going to be 11. And so we end up with 13, and that's our final answer right over there. So we can see that actually rewriting before integrating, doing a little bit of algebraic manipulation, makes integration much more easier. And then next up, we have this indefinite integral right over here. It's a very long, crazy, rational polynomial expression. But honestly, although it looks crazy at first, we just have to observe it a little closely, and we can notice that a lot of these terms, we can just factor in. A lot of these terms may cancel out. And so if we look at the denominator, we notice this pattern, the x cubed plus 3x squared plus 3x plus 1. That is basically just, if you want to go back to the Pascal's triangle or the binomial theorem, this is just the expansion of x plus 1 cubed, right? And then in the denominator, here we have 2x squared plus 4x plus 2. Well, we can factor out a 2, right? And we end up with x squared plus 2x plus 1. And then we can put the dx there. But what is this right over here? This is just x plus 1 quantity squared. And so all we have to do, we can rewrite this now as the indefinite integral of x plus 1 cubed, right? X plus 1 cubed over, I don't know why that line was so large. Okay, let me just, there we go, over 2 times x plus 1 quantity squared, dx. And then we can just cancel out these exponents over here, right? So we end up with this being equal to, we can even take the 1/2 out if we would like, 1/2 times the integral of x plus 1 dx. And then what is the integral of x plus 1? Well, this is going to be 1/2 times, we know that x plus 1, that the integral of x is just going to be x squared over 2, right? We increment the exponent and then divide by that new incremented exponent. And then the integral of 1 is just going to be x. And of course, we can't forget the plus c. We expand that 1/2, we end up with x squared over 4 plus x over 2, and we keep the plus c the same because it's just a constant of integration. And so that would be our final answer right over there. So we started off with this crazy rational polynomial, and we ended up with a very nice and simple equation right over here, very simple quadratic. And so I hope this helps. It's a very crucial concept to learn, rewriting before integrating, and will apply to any integration problem that you're ever going to solve in your calculus experience, I suppose.